So this is the Unit 6 Trigonometry Review, and I have to tell you at this point in time that it's going to start off numbers 1 and 2, but it will change up. It's not all in order, and because of the medium that I'm using will not allow me to put it back in order. So it's all here, it's just in a different order, just pay attention to the numbers. So for number 1 in right triangle SUN, where the measure of angle N is 90 degrees, which of the following statements is always true? So we have a right triangle because the angle N is 90 degrees, and the only time that the two functions are the same is when you have sine of an angle and cosine of its complement. Okay, so we know that in a right triangle, the sum of the two acute angles is equal to 90 degrees, and the sine of one angle is equal to the cosine of the complementary angle. So you can draw a picture if you need to, and a visual might be better for you to see that. And as you can see, these two angles here, angle S and angle U, are the complementary angles. That means sine of S is equal to cosine of U. For number 2, if the sine of angle 4x plus 21 degrees is equal to cosine of angle 2x minus 3 degrees, what is the value of x to the nearest tenth? So in order for sine to be equal to cosine, these two angles must equal 90 degrees. So I'm going to set their sum equal to 90. Combine like terms. So x is equal to 12. And since it's to the nearest tens place, it's 12.0. Triangle BAT is similar to triangle ZIP. The measure of angle T is 90 degrees. If cosine of B is equal to the ratio 4/5, which of the following statements is true? Okay, the first thing that I would do is draw a picture. Where T is 90 degrees. And we have two similar triangles. Make sure the corresponding angles are correct. And cosine of B, so that's this angle here, is adjacent 4 over the hypotenuse of 5. What I can tell you is this, and this is something that's new. So we're going to connect similar right triangles, or the idea of it, with trigonometry. And since B corresponds to Z, we can say that cosine of Z has the same ratio as 4/5 because they are similar. Okay, so in similar right triangles, and with regard to corresponding angles, we know that sides have the same proportion. They're in the same proportion. Okay, so that means the ratios are the same. So if we look at each of the choices, sine of Z is 4/5. Cosine of I is 4/5. Tangent of Z is 4/5, and sine of I is 4/5. So in terms of similar right triangles, let's just talk about this whole idea for a minute. If you look at triangle BAT, we have two sides based on what we were given up here. Okay, and this is a right triangle, We have a hypotenuse of 5, a leg of 4, so we know that the other side, or leg, is 3. And you could either find that using Pythagorean's theorem, or you just know that it's a Pythagorean triple. So 3, 4, 5 is a common one. And since we have the ratio of sides here, we know that cosine of b is 4 over 5. We also know that sine of b is 3 over 5. We know that tangent of b is 3 over 4. And we could do the same thing for angle A. So angle A, cosine of A is 3 over 5. Sine of A is 4 over 5. And tangent of A is 4/3. So those would all be true statements. But we're not talking about BAT. We're using a value for cosine of B. And in using that value, we're going to use the same ratio values because in similar triangles, we know that angle measures are preserved and sides are in proportion. So we know that we're going to have same ratios when sides are in proportion. And as a result of that, we're not stating that the side measurements are the same. We're just saying the ratio of the sides are the same. So since we know that cosine of b is equal to 4/5, we can say cosine of z is also 4/5 because that is a corresponding angle, and with regard to the sides, it's adjacent over hypotenuse, just like triangle BAT. So let's just draw up some other true statements here with regard to triangle ZIP now, based on triangle BAT. So sine of z is equal to 3 over 5, just like sine of b. Tangent of z is equal to the same thing as tangent of b, which would be opposite 3 over adjacent of 4. Now let's do this for I. So cosine of I is equal to adjacent over hypotenuse, so that's 3/5. Sine of I is equal to opposite over hypotenuse. And tangent of I is equal to opposite over adjacent. So let's just check to see again if any of these are here. Okay, so sine of z is 3/5, that doesn't work. Cosine of I is 3/5, choice 2 doesn't work. Tangent z is 3/4, so choice 3 doesn't work. And sine of I, we have as 4/5 right here, so that is choice 4. This works. Triangle ABC shown to the right, well, it's shown below in this case, is dilated by a scale factor of 3, resulting in triangle A prime, B prime, C prime. What is the relationship between sine of beta and sine of beta prime? So beta is another way of representing an angle, okay, just like theta, which we've seen before. It's a Greek letter as well. We don't see it as often as theta, but it does work. So again, going back to similar right triangles, if we dilate something by a scale factor of 3, okay, we're basically distributing that. We're making it bigger through multiplication. So we can't have the same thing, right? If we have a scale factor of 3, okay, we have to multiply something by 3. So this is not going to work. We're not going to be adding by 3. That would be a translation. And if you look at choice 3, we're taking the original picture and we're going to distribute that 3 to it in order to get the dilated figure, which would be this part. So choice 3 is the answer. Okay, so in triangle CAP, the complement of C is P, which statement is always true. Okay, so we're going back to cofunctions again. Okay, so the sum of these two angles must equal 90 degrees. So the trig functions that would be considered equal is the sine of one angle and the cosine of the other angle. So that's choice 1. So in the diagram of right triangle ABC, shown below, AB is 14 and BC is 11. Okay, I'm going to take this out of here because that's not what you have on your review. You have 11 down here. What is the measurement of angle B to the nearest degree? Okay, so we're looking for this angle measure. Given those two sides, I need to set up a ratio along with a trig function. So for angle B, I have its adjacent side and the hypotenuse, so that means I'm using cosine. Cosine of theta is equal to adjacent 11 over the hypotenuse of 14. Since I'm looking for an angle measure, I need to use its inverse function. That's anytime you're looking for an angle measure. And then I will have my theta. And that's 38 degrees. Which expression is always equivalent to cosine of x when you have an angle that's in between 0 and 90 degrees. Okay, so we know that angle measures have to be complementary in a right triangle, right? So if we have x here, then this one has to be 90 minus x. And the only way for trig functions to be equal, we need to have it in terms of cofunctions. So cosine of x is equal to sine of 90 minus x. And the same goes for sine of x is equal to cosine of 90 minus x. So sine of a is equal to 4 over 5. What is the value of cosine of a? We're going to use the Pythagorean identity for this, because we know sine square of a plus cosine square of a is equal to 1. Can you set this up in a right triangle also and have a and possibly b here and maybe c here? And we know sine of a is opposite over hypotenuse, and see that this is side 3 because it's a Pythagorean triple, and be able to find out cosine of a is adjacent over hypotenuse 3 over 5? Yes, you can. But we also want to be functional in using Pythagorean identity because that's going to be helpful for you in Algebra 2 and Trig. So we're going to take 4/5 and plug it in here. We have cosine square of a, that's equal to 1. Simplify 4/5 square and get 16 over 25. And solve for cosine by subtracting 16 over 25 from both sides. We get cosine square of a is equal to, if you don't know how to do fractions, just put this in your calculator. We get 9 over 25. Then we need to take the square roots of both sides. We get cosine of a is equal to 3 over 5 because both the numerator and denominator here are perfect squares. So we get the same answer as we could have done here. So you, again, pick your poison, but this is preferential so that you get used to using it and apply it in trigonometry next year. A Monticello High School student is interested in calculating the height of a flagpole. He stands 50 feet from the base of the flagpole. So let me draw this flagpole. And this kid is standing 50 feet away from him. Okay, so this is redundant. This didn't get worded correctly, so that's going to need to be fixed. He stands 50 feet from the base of the flagpole and measures the angle of elevation from a point 50 feet from the ground. Okay, so that's redundant. To the top of the flagpole to be 68 degrees. So that goes inside here. To the nearest foot, what is the height of the flagpole? So we're looking for this x. So based on this angle measure and the ratio of sides, I have tangent of 68 degrees is equal to opposite x over adjacent 50. So we're going to cross multiply. So 50 tangent of 68 is equal to x. Looks like it is 124 feet to the nearest foot. So none of these answers work. So this is the answer. In the accompanying diagram, DE is parallel to BC. If sine of AED is equal to 4/5, what is the cosine of ACB? Okay, so the sine of AED, we're back to similar right triangles. So we know that with similar right triangles, we have the same ratios in terms of dilation. So with regard to angle AED, we have sine, so that's opposite over hypotenuse. So the cosine of ACB, this angle here, we know that this side is 3. We got a Pythagorean triple. So with regard to C, cosine is adjacent over hypotenuse, so that means we're going to use the cosine of E as the same ratio. So the adjacent side is 3 over 5, therefore cosine of C, since it's a corresponding angle, is equal to 3 over 5. And that's choice 4. So if sine of theta is equal to 7 over 9, then what are the values for cosine of theta and tangent of theta? So again, you can use Pythagorean's theorem in order to find the other values. I'm going to use the Pythagorean identity function in order to use this. So sine square of theta plus cosine square of theta is equal to 1. So I know the value here is 7/9. I'm going to square it. So we get 49 over 81. So let's subtract 49 over 81 from both sides. And get 32 over 81. Just put that into your calculator. Take the square root of both sides. Get cosine of theta is equal to square root of 32 over 9. And we have to simplify the square root of 32. So we know that 16 times 2, that's a perfect square. So it becomes 4 radical 2 over 9. So we have a value for cosine of theta. Now we need to find tangent of theta, and I've run out of room here, so that's crappy. But tangent of theta, if you remember the quotient identity from the lesson, that is sine of theta divided by cosine of theta. And now we have two values, one for sine of theta and one for cosine of theta here. So we're going to take 7 over 9 and we're going to divide that by 4 radical 2 over 9. Okay, so when you're dividing by fractions, you have to multiply by the reciprocal of the denominator. So I'm going to take the denominator and flip it and multiply it to the numerator. The 9's cancel out, and then I get 7 over 4 radical 2. But you can't have a radical in the denominator, so we must rationalize that which you've learned how to do. So I'm going to multiply top and bottom by radical 2 and get 7 radical 2 all over. 4 radical 2 times a radical 2 is 8. So the tangent of an angle, theta, is equal to 7 radical 2 over 8. So our carpenter leans an extension ladder against a house to reach the bottom of a window 30 feet above the ground. As shown in the diagram below, the ladder makes a 70-degree angle with the ground. To the nearest foot, determine and state the distance of the base of the ladder to the wall. Okay, so that means we're looking for x here. Based on this angle measure, I have the opposite and the adjacent, so that means this is the tangent function. X is in the denominator, so I'm going to switch the function of the angle with x. And just put this into my calculator and get what the distance is to the nearest foot, as it states up above. So it is 11 feet. The diagram below shows the plans for a cell phone tower. A guy wire attached to the top of the tower makes an angle of 65 degrees with the ground. From a point on the ground 100 feet from the end of the guy wire, the angle of elevation to the top of the tower is 32 degrees. Find the height of the tower to the nearest foot. So as you can see, we have two triangles here, and more than likely we're going to be using the law of sines. So this triangle right here is our oblique triangle, and we're going to have to use the law of sines with this one. And then the second triangle, as you can see, is the right triangle. Now ultimately we need to find the height of the tower, but we're going to have to use some information from the oblique triangle first before we can do that. So this angle here we can actually find because it is next to the one that's given, 65 degrees, and those two are adjacent to each other on a line, so their sum is equal to 180. So if we subtract 65 degrees from 180, we get a difference of 115 degrees. Which makes sense because you can see that it's an obtuse angle there. I'm going to be looking for the length of this wire here before I can find this value for x. So I have this angle, and this, I'm going to make this y because that's what I'm looking for first. I have this side right here, and I need the angle opposite. I do have two measures of angles inside this triangle, the one outlined in red. So all I have to do is take their sum and subtract that from 180 because the sum of three angles of a triangle, and that's any triangle, is equal to 180. And get my third angle measure, which is across from the 100-foot side of the triangle. And I get 33 degrees. So 100 over sine of 33 is equal to y over sine of 32. Okay, I'm going to cross multiply. I'm going to keep y over here and just put this whole entire thing into my calculator exactly the way I see it in order to get what y is equal to. I wouldn't round this right away. I would leave it to 4 decimal places. So you should have gotten 97.2973. Okay, so now I have a value for this length right here. So y is equal to 97.2973. With regard to this angle in this triangle, I have the opposite and the hypotenuse. So sine of 65 is equal to x, the height of the tower, over 97.2973. Cross multiply. And this is what we're going to round to the nearest foot, which is 88 feet. So the height of the tower is 88 feet. As shown in the diagram below, fire tracking station A is 100 miles due west of fire tracking station B. A forest fire is spotted at F on a bearing 47 degrees northeast station A and 15 degrees northeast station B. Determine to the nearest tenth of a mile the distance the fire is from both station A and B. Okay, so it appears as though we're looking for two sides, this one as well as this one. And we need to round our final answer to the nearest tenth of a mile. We have an oblique triangle. So if we add the 90 and the 15, we get this angle here, which is 105. We have a right angle over here. So that means the sum of 47 and this other angle here is equal to 90. So that means this angle here is equal to 43 degrees. And if I take the sum of 43 and 105 and subtract that from 180, I get the third final angle of that oblique triangle to be 32 degrees. I'm going to need that angle because I have the side that's across from it, which is 100 miles. So I have 100 over sine of 32 is equal to x over the sine of 105. And for my second law of sines problem part, I'm going to use 100 over sine of 32 and set that equal to y over the sine of 43 degrees. Go ahead and cross multiply in order to solve for each of the variables. Okay, so I'm going to bring this over here. So I have 100 sine of 105 over sine of 32 equal to x. And for the second one, I'm going to multiply 100 to sine of 43, all divided by sine of 32, and that's equal to y. So on the left, to the nearest tenths, I get 182.3 miles. And for my y, I get 128.7 miles. Okay, last one. As shown in the diagram below, a ship heading directly toward a lighthouse whose beacon is 125 feet above sea level. At the first sighting, point A, the angle of elevation from the ship to the light was 7 degrees. A short time later, at point D, the angle of elevation was 16 degrees. To the nearest foot, determine and state how far the ship traveled from point A to point D. So I'm looking for this variable right here, the length of this side. Okay, that is a part of this oblique triangle here. These two angles are adjacent and on a line next to each other, so if I subtract that from 180, 180 take away 10 is 170, take away 6 is 164. Okay, and I'm going to find this angle measure in here by subtracting the sum of 164 and 7 from 180, because the sum of three angles of any triangle is 180. That is 9 degrees. That is 9 degrees. I need to find the length of this side. I'm going to label that as y using this angle measure and the side opposite from it. So I have 16 degrees is equal to opposite 125 over the hypotenuse of y. So that means this is sine. The variable's in the denominator, so I'm going to do a switcheroo. And I get to 4 decimal places y equal to 453.4944. Now using that value, for the length of this side, I see that the angle opposite is 7 degrees. So 453.4944 over sine of 7 is equal to x over sine of 9 degrees. Cross multiply, and divide by sine of 7, and to the nearest foot we're going to get a value of 582 feet. And that concludes this review. Good luck on your test tomorrow.